Also, thank you everyone for being here in the last session. So hopefully this is not a difficult talk to follow, so it won't be too taxing after a whole day. This talk is going to be based on a paper called Quantum Free Games with Anand Natarajan at MIT. The topic is quantum free games. So the main idea of this work is to work towards a tighter understanding of several quantum generalizations of the notion of classical free games. So to tell you what a free game is, I first need to tell you what a multi-prover game is. It's also known as a multi-prover interactive proof. So usually in the setting, you have a single verifier who's conventionally known as Arthur and who is PPT bounded. And the setting is you have Arthur interacting with two all-powerful provers called Merlin 1 and Merlin 2. In this, let's just focus on the one round two prover setting. So basically Arthur will send two questions, X and Y, to Merlin 1 and Merlin 2 respectively, and receive two answers, A and B. And then Arthur looks at A and B and decides whether he's going to accept or reject the two Merlins, and that's it. You could also have more provers and more rounds, but this definition will suffice for us. So in normal MIPs, the questions, X and Y, are allowed to be correlated. And let's look at a quick example of why this is useful. So let's suppose that Arthur has like a graph in mind and he wants to know if it's colorable or not. So of course the Merlins know the answer because they're all powerful. So how could Arthur find out? Well, he could ask Merlin 1 for the colors at the endpoints of a random edge and ask Merlin 2 for the color of one vertex on that edge. And then Arthur checks that Merlin 1's two colors are different. That's the colorability property. And that Merlin 2's color is consistent with Merlin 1's answer. So the only way the Merlins can be consistent with each other in this test is if they previously agreed before. Oh, I forgot to say, so in this model, Merlin 1 and Merlin 2 are not allowed to communicate after they receive Arthur's questions. So the only way they can be consistent is if they previously agreed to answer according to some fixed assignment. That's because if Merlin 1's answers depend on the edge that he was given, which is the only way he can cheat if the graph is not actually colorable, then Merlin 2 won't be consistent with him because Merlin 2 can't communicate with Merlin 1 after he receives the questions, and so he doesn't know what challenge Merlin 1 got. Okay, in this way, using this sort of protocol, notice that Arthur can verify even exponentially large coloring instances. That's because it only takes like log n bits to send an edge or a vertex, where n is roughly, the instance size, the size of the graph description. And by verify here, I mean verify whether it's satisfiable or far from satisfiable. So let's just like pretend that the gap is constant. We have classical PCP theorem to help us do that. Okay, so that's a multi-prover game. It's very important in classical complexity theory. MIP2 is equal to next is, one of the most important results. And the techniques in that proof eventually led to the proof of the PCP theorem. Okay, so now let's talk about free games. So in a free game, X and Y are not allowed to be correlated. So basically Arthur has to sample X and Y independently. So note that with this constraint, we can no longer verify exponentially large coloring instances using this consistency test paradigm that I just introduced. For example, in here, the reason is that as the graph grows very large, the chances of getting, so the best you could do is just sort of like this strategy depends on sending an edge and then setting a vertex that's correlated with the edge. It's one of the vertices on the edge, right? Now, if you're not allowed to sample correlated questions, the best you could do is send a bunch of independently random edges to Merlin 1 and a bunch of random vertices to Merlin 2 and just hope for collisions. But as the graph gets really big, that's going to be pretty bad. So we expect to send, using the birthday paradox, we expect to send about root n vertices or edges before we get any collision. Where n is roughly the number of vertices or edges in the graph, we'll just assume that like the number of edges is O of the number of vertices, for 3 coloring, and generally that tends to be where the hard instances are. Okay. So since the work Arthur does scales as root n, where n is roughly instance size, we can only hope to verify polynomially large instances of 3 coloring using this strategy, so we're sort of back to back to MP. And this intuition was formalized by Aronson, Impagliazzo, and Moshkovitz in 2014. So they proved that AMK is equal to AM for any polynomial K, and K, so AMK is basically just the free game version of MIP. So you have this freeness constraint on the questions with K provers. So for any polynomial number of provers, AMK is equal to AM. So AM, as we know, is equal to MP under plausible assumptions. So under plausible assumptions, introducing this freeness constraint results in an exponential decrease in deciding power from next to MP. Okay. But there is something you can, it might well be that AMK is just equal to MP, but there is something you can do using the AMK model that you couldn't do using a single prover, and that is verify using only about root n bits of communication, verify a 3 coloring instance. So the protocol, we actually already described it. It's exactly this. You just send a bunch of random vertices, a bunch of random edges to melon 1, a bunch of random vertices to melon 2, and hope for collisions, and then do the usual check. Okay. So if Arthur could do this if he could use only root n bits of communication and do it by interacting with only one Merlin, he could solve 3 coloring in sub-exponential time, because he could just brute force search over that Merlin's possible answers. And we don't believe that there's this thing called the exponential time hypothesis. We don't believe it's possible to solve 3 coloring in such a short time. The reason you can't brute force search when there are 2 provers is because it's sort of harder. Like in this case, you just need to find any assignment for the Merlin's answer that satisfies Arthur. In the other case, you also have to do something about the correlation. You have to make sure that your space search is a little constrained because, there's always going to be something that satisfies Arthur. You just need to fill in the edges with different colors, right? So just brute force searching isn't enough in that case. Okay. So I'll talk first about this quantum generalization of classical free games called QMA2, and then I'll move on to another one called AM star. Okay, so what is QMA2? Aronson, Impagliazzo, and Moshkovitz were actually inspired to work on AM2, classical free games, by a quantum class called QMA2. So QMA2 is the same as QMA, which is quantum MP. So instead of having a classical verifier with a classical witness, you have a quantum verifier and a quantum witness. QMA is the same. QMA2 is the same as QMA, but with 2 quantum witnesses instead of 1. Alternatively, you can consider this as Arthur gets given 2 witnesses by 2 non-communicating and unentangled Merlins. So of course this would be silly if you were to apply this to MP, right? Like what does it mean to have 2 classical witnesses? You could just join them together and you have 1 classical witness. But it's not silly to apply to QMA necessarily. And the reason is that you're just supposed to imagine, Merlin 1 gives you 1 witness and Merlin 2 gives you another one. And the reason is you can guarantee in this setting that the 2 witnesses you get are unentangled. Now, if unentanglement were a property that Arthur could check for himself efficiently, then we wouldn't, QMA2 would be obviously equal to QMA, but we don't know how to check that property. So you can't simulate a QMA2 proof in QMA necessarily. Okay, so the complexity of QMA2 is not well studied. The best upper bound we have is next, the best lower bound is QMA. And the most compelling example of something which sort of gives some weak evidence that QMA2 is not equal to QMA is, guess what? You can verify MP in sublinear communication, in this case, sublinear number of qubits of communication. And that's not a coincidence. So to understand why the AM2 classical free game and the QMA2 protocols are so closely connected, let's look at, how would we convert the AM2 protocol we described earlier for verifying 3 coloring into a QMA2 protocol? Okay, I lied. Actually, let's do it in a QMA-K protocol where K is roughly root n, and is again the size of the instance. So we just have a lot of provers instead of 2, right? Okay, so let's recall how the AM2 protocol for 3 coloring works. Arthur sends uniformly random edges to melon 1 and uniformly random vertices to melon 2 and hopes to get collisions. So let's just establish notation here. We'll use C of E as a shorthand for the colors assigned to the endpoints of an edge. We'll use C of E as shorthand for the color assigned to one vertex V. Okay. So we want to turn this whole protocol into a QMA-K protocol, where K is roughly the number of edges or vertices that we're sending here and here. It doesn't have to be equal, but let's just say they are. So we need to turn each question and response pair into a single quantum state, because in the QMA2 model, we only have one-way communication. Merlin sends stuff to Arthur, and we don't get to say anything back, right? Okay, so let's say we have 2K Merlins. Let's give ourselves a little bit of leeway, right? The K, again, is going to correspond exactly to the number of edges or the number of vertices that Arthur would have sent in the AM2 protocol. And let's divide them into left Merlins and right Merlins. So we could have all the left Merlins send Arthur this state. So all first K Merlins send this state where, okay, so this is a superposition. There's a bunch of weights. And it's a superposition of edges in the graph. The components of the superposition are these two registers, where the first register is the name of an edge. The second register is a color assigned to that edge. And this is a superposition over all the edges, and there are some weights here. And all the right Merlins are going to send Arthur this state, where it's the same, but now we have vertices, right? And color assigned to a vertex and some weights, right? Okay, so if the alpha e's are all approximately equal to each other, which means they must be equal to this, and same for the alpha v's, then measuring these states in the standard basis is equivalent to asking a uniformly random question of the Merlins and getting it the answer. So that's basically the key insight behind this protocol, which was developed by Chen and Drucker in 2010. This is just a superposition over answers, questions and answers, basically. The question, the answer, the question, the answer, right? So this is a way to verify three-coloring in about root n log n qubits of communication. The log n just comes from, these states are not actually constantly long, they're about log n qubits long, and with about root n qubits. So Chen and Drucker developed this thing called the uniformity test, which morally allows Arthur to certify that all of these weights are actually approximately equal to each other. So it'd be bad, obviously, if the Merlins could somehow give you states that have unequal weights, right? They could just weight the parts of the graph that are actually colorable, even if the whole instance is not, right? So you need something to certify that they're approximately actually a uniform distribution, and there's this uniformity test to do that. But then, of course, your whole protocol hinges on the uniformity test, so the limitations of the protocol are also the limitations of the uniformity test. So in particular, the uniformity test requires short answers. So in this case, we only have a constant number of colors in the answers, right? So this is like three possibilities, so we can express it in a constant number of bits. The Chen-Drucker analysis of the uniformity test also requires unentanglement between all these separate edge states and vertex states that, these 2K Merlins are supposed to send us. And that's why you need so many provers, because you want the unentanglement guarantee between all of them. Okay. So we've seen a protocol to verify three coloring in roughly root n bits of communication in AM2 and also in QMA2. So is the root n necessary? Is it, optimal? So there is some evidence that it is. For example, Brandau, Christanel, and Yard in 2010 find a way to convert any QMA2 protocol for MP where the verifier does not do entangling measurements into an algorithm for 3-SAT, taking approximately 2 to the communication squared time. So that means if you do better than root n, then you're solving SAT in like sub-exponential time, and that would be bad. We don't believe that's possible. Okay, but what do I mean by verifier does not do entangling measurements? You're supposed to have this sort of model in mind. So before, it's the same. You have two Merlins. Each one gives you one state. But now you should imagine that the verifier is also composed of two entities, each of whom receives one of the two states that the Merlins are going to send. So I call them Arthur and Lancelot. You're supposed to imagine that Arthur and Lancelot measure these states that they receive separately, and then they do some sort of classical computation to decide on their decision, but they're not allowed to do entangling measurements that cross these two states. So I said this already. Okay, maybe at least in this restricted setting, we would have a tight understanding of what's going on. That's not the case because, this result, BCY, is for two-prover protocols. The lower bound is for two-prover protocols, and the Chen-Drucker protocol has about root n provers. So we didn't know whether BCY was tight. And there is a way to get it down to two provers. This work by Haro and Montanaro from 2010, but that requires entangling measurements, so it doesn't work for the BCY setting. Okay. So what do? There's sort of an obvious thing to do when you have the Chandraka protocol and you want it to be two provers. Well, you can just like stick all of the left Merlin states together and stick all of the right Merlin states together, and now you have two provers, right? So, you know, we were like, this has been open for like 10 years. There's no way that would work. That's so stupid. We kept trying to find counterexamples, but we failed. So then we tried to prove that was sound, and that worked. So this is our first contribution in this paper. We reanalyzed the Chandraka uniformity test to show that even if we don't have any unentanglement guarantee between the copies of all of those edge states and vertex states the Merlins are supposed to send us, it satisfies a form of soundness. So it's not as strong as the one that Chen and Drucker get. We can't, like the Chen Drucker say, oh, the amplitudes alpha, E are basically all equal. That only makes sense when the copies are unentangled, and we can't guarantee that. But we can guarantee that measuring the question registers in the standard basis generates approximately uniform randomness. So, you know, that's sort of exactly the intuition that we wanted to satisfy, right? When we had this AM2 protocol, we basically wanted to simulate Arthur generating this honest, independent randomness by sending these quantum states. And that's exactly what the security property that we prove. Oops, okay. Yeah. So we show that BCY is tight up to some log factors. That's technical. And there's a bonus, which is our analysis is arguably more accessible than the original Chandraka analysis. It's shorter and, you know, maybe a little easier to digest if you know the central ideas. Okay, so in the remaining time, I will go through the other two results in this paper. I chose to focus more on the first one. You know, which one is more interesting, I think, depends on your perspective. But the first one is sort of more accessible, but I'll briefly summarize the results, the other results. So you know, we saw one generalization of classical free games, which was QMA2. But there's another one, which is maybe more obvious, which is just, okay, have the normal free game model, you know, X and Y must be unentangled, uncorrelated, the questions must be uncorrelated. You have two Merlins, you know, you send questions to them, they give you answers, but now just allow the Merlins to share entanglement. This should be familiar, right? This is exactly the transformation that takes classical MIP to MIP star. Recent results have shown that MIP star is equal to RE. So Aronson and Pagliazzo and Moshkovitz also showed that AM2 is weaker than MIP2 in the classical world under plausible assumptions, right? So is the same true of AM star 2 and MIP star 2, like the entangled versions of AM2 and MIP2? So we show that in the quantum case, the answer is no. In fact, AM2 star is equal to MIP2 star, equal to RE. So this means that free games are as powerful as general games in the entangled case, even though the freeness constraint leads to this exponential decrease in deciding power in the classical case. So we show this by showing that MIP2 star with constant size questions and polylog-sized answers is equal to general MIP2 star. So the MIP2 star equals RE result had polynomial-sized questions and polynomial-sized answers. We just get the same result, but with very short questions and relatively short answers. Now, if the questions are constantly sized, then getting collisions is very easy. So, you know, this is why you can naturally generalize this to AM2 star being equal to RE. Okay. So the previous best lower bound on AM star K, where the K is the number of provers as before, is that it contains NP. And this was for O over M provers by Brandau and Harrow in 2013. So why are we able to do so much better? It's because we can leverage the powerful tools which were developed by the authors of MIP star equals RE, which are based on self-testing. So self-testing allows us to force the provers to introspect, which basically means, this is terminology developed by these authors, basically means that they can generate their own long questions when they play an entangled game. We can force them to do that using self-testing, which allows us to avoid having to send very long questions in order to achieve a constant probability of collisions, which is the problem that we had before with sort of trying to simulate MIP protocols in AM2. Okay. So the last set of results is some lower bounds on MIP star 2 and AM star 2. which are equal. So we showed that MIP star 2 with constant size questions and polylog sized answers is equal to general MIP star 2. So the question, maybe a natural one is, can we do better? What is the smallest possible amount of communication in an MIP star protocol that can decide RE? So for example, with constant questions and log n sized answers, can we decide RE? We show that the answer is no. So using a link to cosmograph complexity, we show that any MIP star protocol deciding RE must use at least O of log n bits of communication. So basically, in more detail, how do we do that? We show that any MIP star protocol deciding RE in a smaller amount of communication can be simulated by a deterministic Turing machine with advice, with some well quantified amount of advice. Then we just prove a lower bound against deterministic Turing machines with advice. So we show basically that a lower bound for the amount of advice that any deterministic Turing machine running in time 2 to the poly n must use to decide exp. So the conclusion there is that you can't have an MIP star 2 protocol with too little communication, or you could convert it into a deterministic Turing machine that uses too little advice to decide exp. And exp is contained in RE, so the result follows also for RE. So interestingly enough, this is not quite tight. As I said before, our upper bound is constant size questions and polylog sized answers. So the gap is like polylog versus log. And we think that if you could recover a quantum sound PCP for MP, then you could make it tight by lowering the upper bound. So we do think that the upper bound is the one that can be tightened, but we leave that as an interesting direction for future work. So that's basically all I have. Thank you.
So thanks a lot for a fantastic last talk of the conference and really nice results. If I remember the Montanaro-Haro result, QMA-K to QIP2 result, right? As well as needing entanglement measurements, they also, because you can't amplify, they have soundness, they can't maintain the soundness and completeness. I guess somehow this is because you don't use that result, you don't suffer that in your case. Is there any intuition why?
Wait, sorry, can you repeat, what do they not suffer? What do they suffer that we don't?
So if I remember right, you get QMA-K to QMA2 in their result, but you don't keep the same soundness and completeness parameters.
I see. So, okay. They do it with this sort of swap test thing, right?
Yeah.
I don't know if there's an intuition. It's more like it's just sort of different, right? We're not doing anything like trying to simulate their stuff in without entangling measurements. We're just saying, okay, well, actually, Chandraka was sound all along, and so I don't know if there's an intuition for why it's better than that.
I guess I could flip the question. Do you think there's any hope of managing to prove QMA-K to QMA2 without losing soundness and completeness using your techniques?
No. Our techniques are just in some sense, it's sort of what Chandraka should have done. Our proof is sort of, I think, the right proof to have here. And the original analysis was sort of relying on the unentanglement in a way that's not really natural or necessary, I think. So, yeah. Sorry if it's not a very satisfying answer.
Thanks a lot for the talk. I was wondering, so when you talk about unentanglement, you mentioned that if I could test whether something is unentangled or entangled, then I could simplify. Is it here really about being a tensor product versus being not a tensor product? Or could you have something like being a tensor product versus having some lower bound on the mutual information of epsilon, some gap, something like this?
Yeah, I think it's gapped. If you could prove strong enough, it is quantitative, QMA2 is defined, like, basically you want to be able to simulate or check the unentanglement enough that it sort of doesn't screw you up too much if you wanted to simulate it in QMA, right? So if you could prove strong enough sort of monogamy of entanglement bounds, that would also work. And those are definitely, like, there's a quantitative threshold. So, yeah.
Thanks.
Last question. Your last session for 4 years. Okay. If not, let's take Tina or the other speakers in the